Hey y'all, welcome back. Today in class, we did a little bit of AP test review, reviewing the key concepts from this unit and some key ideas from last semester. In this homework, we are going to just do a little bit of mixed practice, mostly focused on what we've been talking about in this unit. So let's get started. Number 1 says, given that g prime is equal to f of x, or in other words, the derivative of g is f, determine each of the following. A says use a left Riemann sum in order to approximate the average value of g of x over the interval 0 to 8. So we want to find the average value of g of x, or at least approximate it, and we're going to use the left Riemann sum to approximate the integral that is in the numerator of that average value formula. So typically to find the average value, you're going to find the integral from, in this case, 0 to 8 of g of x dx, and then divide that by the difference of those two values, 8 and 0. Now, because we don't have any information about what g actually is, other than the values that are given in the table, that's why we're sort of stuck using this estimation to actually evaluate it. And there's a couple of different Riemann sums that we could use. This particular one is asking us to use the left Riemann sum. So we'll use the left-hand partition when determining what the height of each rectangle should be. So let's just start figuring out our intervals and all that for the Riemann sum. The first interval, jumping around here, sorry, is going from 0 to 1. So the width of that interval is just 1. The width of the second interval is 4. And the width of the third interval is 3. So those are essentially the bases of the rectangles that we're going to be adding the areas of. The heights will be determined by g of x, and in particular, the left partition. So that first rectangle, we're going to have 1 times -3. The second rectangle will be 4 times 4. And the third one will be 3 times 6. So this will not equal, let's fix that, approximately equal to 1 times -3 plus 4 times 4 plus 3 times 6. That's going to be the approximation for the area underneath that curve between 0 and 8, divided by 8. And that's a pretty good answer. I think we can simplify this because these numbers aren't that bad. So I'm just going to, let's see, -3 times 1 is -3. 4 times 4 is 16. 3 times 6 is 18, all over 8. Suppose we can go to equals at this point because that does equal the previous statement. 13 and 18 is going to be 31 over 8. So for part B, we've got the integral from 0 to 5 of fx dx, and we still don't have really enough information about f of x to find that exactly, except for the fact that we know some information about its antiderivative. Now, since f is g prime, that means that g is the antiderivative of f. Okay, let me say that again. F is the derivative of g. So the antiderivative of f is g. Sounds kind of weird when you say it, but that means that since the antiderivative of f of x is g of x plus c, we're going to substitute in 0 and 5. And we can do this because of the fundamental theorem of calculus. And so this will equal g of 5 minus g of 0. And we can find those values in the table. So g of 5 is 6. G of 0 is -3. So this is going to be 6 minus -3. 6 plus 3 is going to be 9. So kind of interesting here that because we have, the sort of the these specific values of the antiderivative of f, we're able to exactly find the definite integral from 0 to 5. All right, part C, we're asked to find the integral of g prime. And so remember, g prime, that's really just f of x, right? So these are the same function, just named differently. So we can use the fundamental theorem, that part 2, just like we did in part B, and rewrite this as g of x plus c from 0 to 5. Yep, 0 to 5, sorry, from 1 to 8. Still stuck thinking about the last problem. And that'll equal g of 8 minus g of 1. We can find those values in the table once again. G of 8 is negative 5. G of 1 is 4. So we have negative 5 minus 4. And look at that, we get negative 9. I'm going to erase some of this so we don't need to look at that, get distracted by all these other values. Letter D says determine the average rate of change of g of x on the interval 0 to 5. Okay, or 0 to 8. So here we're finding the average rate of change, which is different than finding the average value. So in part A, we looked for the average value. In this case, we're looking for the average rate of change. And so to find the average rate of change, when you see that phrase, rate of change, you should be thinking slope. Okay, and so to find the average rate of change, we're just going to use the slope formula. The classic slope formula from back in Algebra 1 is y2 minus y1 over x2 minus x1. But we're going to think about it a little bit differently. Since we're talking about g of x, we're going to have g of 8, which is like our y2, our second y value, minus g of 0, which is our y1, over 8 minus 0, or the x2 minus x1. So from the table, we can determine that g of 8 is negative 5, g of 0 is negative 3, so we'll have negative 5 minus negative 3, which would be the same thing as negative 5 plus 3, over 8. Negative 5 plus 3 is negative 2, so we get negative 2 over 8, which reduces to negative 1/4. Number 2 wants us to evaluate the derivative of the integral of this function from 0 to 2x cubed. Now, I do not believe that we are ready to find antiderivatives of this expression. I don't really think we have the tools yet to do that. But the good news is we don't have to. The first part of the fundamental theorem of calculus, which is really the second part that we discussed in this unit, says that we can go ahead and just we can evaluate this by substituting in that upper bound into t. Okay, and just basically replace the t with 2x cubed. So we have the square root of 2x cubed squared plus 2 times 2x cubed, all that underneath that square root. We could simplify that a little bit, but I'm just going to leave it the way it is. There's really not a lot of advantage to doing that. If it were a multiple choice question, you might write this as the square root of 4x to the 6th plus 4x cubed, but I'm not going to bother with that. Now, we're not done here yet. That's just the first step, is to substitute that upper bound in. We do also need to multiply by the derivative of that upper bound. So 2 times 3 would be 6, and so we're going to multiply by 6x squared. And so there you go. Number 3 says, given the function f of x equals, and then we have this integrally defined function. Not sure if that's what we want to call it, but that's what I'm going to call it. And it says determine all intervals for which f is decreasing. Okay, so this is a little bit of a different question than what we've seen so far in this unit, but in class we reviewed what it means for a function to be decreasing. So in order for a function to be decreasing, what that means is that the slope has got to be negative, or in other words, f prime has got to be negative. So we're going to be looking for the intervals where f prime is negative. And to find those intervals, we're going to create a sign chart for f prime. And so what we need then are the critical values, which are the values that make the function either equal 0 or undefined. So let's first find those critical values. Okay, and the critical values are going to occur anytime the derivative is equal to 0. So you know what? Before we even get to those critical values, let's find out what the derivative is. So f prime is going to be defined as the derivative of this integral. And so because our upper bound here is just x, I don't have to worry about multiplying by the derivative of x. I mean, technically, yeah, we're going to do that, but the derivative of x is just 1. Whenever it's just x, we're just going to replace these t's with x. So f prime would be x cubed plus 15x squared minus 54x. All right, so we need to know when is f prime, or where is f decreasing? In other words, where is f prime negative? So now we're going to find our zeros, find those critical values. And we find those by finding x values that make the function either 0 or undefined. Now, because this is a cubic functions have a domain of all real numbers, so this will never be undefined, but it may be 0. So we're going to find out what x values make this function 0. And we can solve this by doing a little factoring here. We can factor out an x as a GCF and be left with x squared plus 15x minus 54. Then we can factor that trinomial. If I think of, I'm trying to think of two numbers that multiply to give me negative 54 and add up to positive 15. And factors of 54 will be, let's see, 154. I'm thinking 9 and 6. Yeah, and if they're both, well, hold up. No, maybe that won't work. 9 and 6. How about 3 and 8? You know, with 9 and 6, we can kind of break that up to, let's see, 18 and 3 is what I'm thinking. 18. Does that work? 18 and 3? Hold up here. 18 and 3. Yeah. So we could do, I'm going to do x, well, which one would have to be positive here? I guess 18 would have to be positive. X plus 18 and x minus 3. So now we've got three critical values. Right? We've got one at x equals 0. We've got one at x equals negative 18. And we've got one at x equals 3. So those are going to be my three partitions of the domain here for f prime. So negative 18, 0, and 3. And I'm trying to figure out where is f prime negative. So what I'm going to do is plug in a representative from each interval here into the factored form of the equation, just because testing it without a calculator is going to be a lot easier with the factored form. And so let's start with a number like negative 20. If I substitute in negative 20 into x, I'm going to have negative, because, well, negative 20 is negative, times a negative times a negative. Negative times a negative times a negative is negative. So that means that f prime is negative from negative infinity to negative 18. And now now I'm not expecting any repeated signs here, because none of the zeros have an even multiplicity. So I'm expecting the sign to alternate here. And if it doesn't, I need to go back and check my work. So it is tempting to just say, okay, well, because there's no multiplicity on these zeros, it's just going to be minus plus minus plus. And that's probably going to work, but I still want to test the intervals anyway, just to make sure that maybe in case I made a mistake somewhere. So if I plug in a number like -1, I'm going to get a negative times a positive times a negative, which will be positive. So far, so good. We are getting that alternating sign. And then if I substitute in 1, that would be a positive times a negative, which is negative. We're looking pretty good here. The fact that the factoring worked out so nicely kind of makes me think that we're good, but it is nice to see the signs alternate when we expect them to. If I substitute in 5, I'm going to get a positive times a positive times a positive, which is going to be positive. So we can see we've got two intervals where f is going to be decreasing. One is going to be, and let me just write it like this, f is decreasing on the interval infinity to -18 and the interval 0 to 3. Now I'm kind of out of room. It didn't specifically ask me to justify my answer here, but if you need to justify your answer, the justification is really this right here, is that it's decreasing on those intervals because f prime is negative on those intervals. So I'm just going to make a little note here that this is the justification. Justification. There we go. Okay. Yeah, so let's take a look at number 4. It says, given the function f of x, and again, we have a function defined by an integral of t cubed minus 18t squared plus 81t. And it's saying determine all x values for which f has a point of inflection. Okay, so this was another vocabulary term that we talked about in the notes. A point of inflection is going to be anytime f double prime changes sign. In other words, when the concavity of a function changes from being concave up to concave down or vice versa. This can happen when a subcritical point, let's just leave it at that. A point of inflection happens anytime the concavity changes. In other words, f double prime changes sign. Let's write it like that. F double prime changes sign. Now we don't really care if it's changing from positive to negative or vice versa. Either way, it's going to be a point of inflection. So we are going to have to create a sign chart like we did in the last problem, but we'll do it for f double prime. So let's start with f prime, because we can't find f double prime until we find f prime. And we're going to use the part 1 of the fundamental theorem to do that. We're going to substitute in the x to everywhere where we see the t's. So we're going to have x cubed minus 18x squared plus 81x. One thing I like to point out here with these problems, number 3 and number 4, notice how the lower bound makes no difference. We don't refer to that at all. And we talked about that a couple days ago, why that is. And it has to do with the fact that when we differentiate a constant, it always equals 0. Okay, back to the problem here. So we got f prime, but we need some information about f double prime. So we're going to have to differentiate f prime. We could just use power rule here. 3x squared minus, 2 times 18 would be 36. And then plus 81. Now let's find our subcritical values here, which will basically find the same way that we did in number 3, just for the second derivative instead of the first. Okay, we're going to be looking for where the second derivative is either 0 or undefined. And just like with number 3, if your function is a polynomial, it'll never be undefined. So we really only need to consider where it's 0. But if you ever have a problem where you have a vertical asymptote or maybe a hole in the graph where the function actually is undefined, then you'd have to consider that too when making your sign chart, and use those values where you have those vertical asymptotes as partitions on your line. So here we don't have a GCF that involves x, but we could factor out a 3. Or what might make this even easier is instead of factoring out a 3 as a GCF, is just to go ahead and divide both sides by 3, because 0 divided by 3 is 0. And then we could just divide the right-hand side by 3 and just drop that 3. So we get x squared minus 12x plus, what would it be, 27? And does that factor? 27, that'd be 9. Oh, yeah. So that'd be x minus 9 and x minus 3. So we've got two subcritical values, one at x equals 9, one at x equals 3. Those are going to be the partitions for my number line. And now I'm going to choose representatives from each of these three intervals and find out whether or not the second derivative changes sign. Now, I am expecting the sign to change at both of these numbers, not because that always happens, but because with the polynomial, with this particular polynomial, there's no even multiplicities on any of the zeros. So I'm pretty confident that's going to change on each one because of that fact. So yeah, let's just plug in a number like 0 would be in that first interval. And I'm going to, again, use the factored form here because it's just easier to value in your head, I think. 0 minus 9 is going to be negative. 0 minus 3 is negative. A negative times a negative is a positive. And between 3 and 9, we can plug in a number like 5. 5 minus 9 is negative. 5 minus 3 is positive. Positive times a negative is negative. I am getting that alternating sign pattern here again. Now, if I had like a function like x plus 2 times x plus 2, something like that, where you had a multiplicity that was even, I would not expect the sign to change at that 0. Just a little heads up there. So it doesn't always alternate, is I guess what I'm saying. If I plug in a number like 10, we're going to get a positive times a positive is positive. So sure enough, f double prime is going to change sign at both x equals 3 and x equals 9. So we've got, so let's just answer our question here. F has points of inflection at x equals 3 and x equals 9. Now, if for some reason the question asked for like the coordinates of the point of inflection, you'd have to plug in these x values back into f of x to find the y values of those points of inflection. So you don't plug it back into f double prime. Instead, you plug it back into f if you need the coordinate of f. This doesn't ask for that, and actually I think it would be doable, but that would be a lot more work if I were asking for that y value also. In this problem, just like also in number 3, it does not ask for the justification, but you really do want to be thinking about how would I justify this answer in the case that they do ask for it. And the justification is right here. It's the fact that f double prime is changing sign. That's where the point of inflection occurs, and so that's how we know for sure there's going to be a point of inflection at 3 and 9. So this would be your justification if it asked for it. Okay, let's look at number 5. It says the graph of function f in the figure below consists of line segments and a quarter of a circle. So it looks like that quarter of a circle you can see is that first piece right here. That's the quarter circle. And then all the rest of them are going to be straight line segments. Part A wants the derivative of g. So since g is defined up here, okay, what we really want is the derivative of that. We want the derivative of the integral from -1 to x of f of t. I think rewriting it like this can kind of help you see that, hey, this is just a fundamental theorem of an FTC1 problem, if you will. And so we could just substitute in x for t, and that's going to be, oh, wait, I'm sorry. No, that is correct. Sorry. Whoa. There we go. So that's just going to be f of x. Part B is looking for the second derivative of g. So that's going to be the derivative of f. It's going to be f prime. Part C is looking for g prime of 3. So we said before, g prime of x is just f of x. So g prime of 3 is going to be, here we'll write it like this, g prime of 3 is equal to f of 3. And we can see on the graph, f of 3 is negative 2. G double prime of 4 is going to be the same thing as f prime of, negative 4, not 4. And so if we want f prime, we're looking for the slope. If we just want an f of x, that we're identifying the y value, like in part C. But if we're looking for f prime, or the value of f prime at negative 4, so let's take a look and see what's happening at negative 4 right here. That's looking for the slope. And so this is going to equal the slope of that segment. So let's just take a closer look at that segment there. It looks like we've got a rise of 1. That's my delta y, or my change in y. And then my run is 1, 2, 3, 4, 5. That's my delta x, or my change in x. So the slope, which is rise over run, or delta y over delta x, change in y over change in x, is going to be 1/5. Letter D wants g of 5. Now, g of 5, we're going to have to go back to the original function. Let's clean this up a little bit. The original function is up here, the thing I got circled. And so we're just going to substitute in 5 for x. Don't substitute it in for t. It's got to be just the x. So g of 5 is going to equal the integral from negative 1 to 5 of f of t dt. So to evaluate this, we're going to first, we're going to plug in 5, we're going to plug in negative 1, using that fundamental theorem. And then I'm starting to realize, we're not going to be able to find the antiderivative of this very easily. We don't want to break this piecewise function into an equation or anything. So I think what we really want to do here is think about this more geometrically and evaluate this as the area from negative 1 to 5. So the area bounded between the curve and the x-axis as a signed area, meaning the area above the x-axis will be positive, the area below the x-axis will be negative. So here's negative 1, here's 5. So I've got a little bit of positive area here, and quite a bit more of negative area here. Okay, I think maybe a highlighter is a more appropriate tool here. So this area right there, and then we've got all this area. Now both of these shapes are triangles, so we just need to do 1/2 base times height on each one of them. So this is going to equal, I'll start with the positive area, 1/2 times the base, which is 1, times the height, which is 4. And then with that larger triangle, the one that is going to be considered negative area, so I'll subtract this. The base is 5, so we have 1/2 times 5 times the height, which is 1, 2, 3, 4. So let's see, half of 4 is 2, and half of 20 is 10. 2 minus 10 is going to be negative 8. Part E says determine all values of x on the interval negative 9 to 9, where x has a point of inflection. Okay, a point of inflection. Again, that's where g of x, or not g of x, but g double prime x changes the sign. Okay, now let's think about what g is. If g prime is f of x, we established that in part A, and g double prime is f prime, if we're looking for where g double prime is changing sign, what we're really looking for on the graph is where f prime changes sign. Now, f prime is the derivative of f, or in other words, the slope of f. So we want to look for where's the slope changing from positive to negative, or vice versa. Now we can see on the graph of f that the slope is positive, 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 till we hit x equals -1. And then we've got a negative slope from -1 to -4, and then after, to 1, and then after 1, it's all positive again. So there are two locations where the sign of f prime is changing, and that's going to be at x equals -1 and at x equals 1. And the justification for that is because g double prime changes sign. That is a little bit of a, I think that's kind of a hard problem to put your head around. It's really easy to get kind of confused between the f of x and g of x. But if we, once we find g prime and g double prime at the beginning, we have that relationship between g and f. So it makes it a little bit easier when you establish that up front. Okay, last part to this. F, write the equation of the line tangent to the graph of g of x at x equals -6. Okay, so it's been a while since we did this. Equation of the line. All the equations of the line tangent, all the tangent line equations, the normal line equations, they're all going to be basically set up the same way, which is with your point slope formula. Y minus y1 equals m times x minus x1. We did this so much in the first semester. It's been a little while since we've done it here in the second semester, but I don't want you to forget how to do that. And we want to find the equation of the line tangent to the graph of g, which is not the graph we see here, to the graph of g at x equals -6. So we have the x coordinate of a point, right? The point is going to be -6 comma something. It's going to be -6 comma g of -6. Let's go back up here. What is g of -6? G of -6 is going to be the integral from -1 to -6 of f of t dt. Ooh, this is kind of a juicy problem here. Okay, so we got to find the area between -1 and -6. Those boundaries are backwards, so this is going to equal the opposite of the area between -6 and -1 of f of t dt. So if we go look at the graph from -6 to -1, that's going to be, let's erase everything else that we've marked up over here. Uh-oh. What's going on here? There we go. We want the area underneath the curve from -6 to -1, but we're going to consider that area negative. Okay, I know it's above the x-axis, but because those boundaries were backwards, we do have to flip the sign on that area. So we've got a basic trapezoid here where we're going to average the two heights and then multiply by the base. So the base is, let's see, is going to be 5. Times the average of the heights. Now the heights are 3 and 4, so the average is going to be 3.5. So we have -5 times 3.5. That's going to be, let's see here. 5 times 5 is 25. 5 times 3 is 15. So 5 times 3.5. All right, if my mental math is okay here, it's going to be 17.5. So -17.5. Now that is just the y coordinate of the point. So -6 comma negative 17.5. But that's just the point. We also need the slope. Okay, the slope is going to be given by g prime at negative 6. So g prime at negative 6, if we go back up to part A and also look at C for an example, we can evaluate this by just finding the value of the function at negative 6, the function f, which is actually pictured. And so if I look at the value of f, where x is negative 6, see that right here, let me point an arrow to it. That's going to be, let's see, what is the value there? It's going to be 3. So the slope's 3. So let's finish this one off. This one took a little bit more work than I was expecting. Y minus negative 17.5, so it's going to be plus 17.5, equals the slope 3 times x minus negative 6, so plus 6. I think this probably is the most complicated equation of the tangent line problem I think we've seen all year, if I'm being honest. I can't really think. Maybe there was one that was a little complicated last semester, but I can't really think of one that had as many steps and as many different little twists and turns as this one. Okay, let's do the last problem. Number 6 says a function f is shown below. If g is the function defined by, and again, we've got this function defined as an integral. Seen a lot of these. Order the following from least to greatest: g5, g prime 5, and g double prime 5. So let's see if we can evaluate each one of these, and we'll evaluate them all separately. So let's start with g5. Okay, so g of 5 is going to be the integral from negative 5 to 5 of f of t dt. In other words, we want the area underneath the curve between negative 5 and 5. So we've got, oh, wait a minute. We're not going to be able to actually do that. Let's back this up a little bit. We're not going to be able to calculate this without knowing what that function is, and we don't know that function. So we're going to have to think about, I think where this is probably going to go is we're not going to be able to find exact values for each one of these, but we can compare. I have a feeling, because we've seen a couple of problems like this in the past, where each one of these things, g5, g prime, g double prime 5, are either going to be like 0, positive, or negative. Not totally sure, but I just want to label this area here just to kind of get a feel for what's happening between negative 5 and 5. So all the red area here is going to be negative. All the green area is going to be positive. I'm only going up to 5. Okay, now just looking at this sketch, it seems pretty clear to me that that area under the curve, there's going to be more negative area. So g prime 5, I'm not sure exactly what this equals yet. We'll come back and see if there's any way to kind of figure that out exactly. Maybe we could do a Riemann sum or something if we really have to. But for now, all I'm going to say is that it's going to be negative. Okay, let's talk about g prime. Okay, g prime of 5 is going to be the derivative of this function. So let's go ahead. You know what? Let's find g prime before we evaluate it at 5. So g prime is going to be the derivative of this function, which will be, well, just f of x. So what we need is if we're going to find g prime 5, what we really want is f of 5. It's asking for the y value when x is 5. And we can see this one we're actually going to be able to find pretty easily. We can see this one's labeled. It's not, even if we're not 100% sure, it sure does look like the height there is 2. So this looks like it's just 2. So we've got a negative number, some negative number, and g prime of 5 is 2. So I'm not exactly sure where g double prime is going to end up. But for right now, I can say certainly that G prime is bigger than G of 5. So G prime 5 is bigger than G of 5. And that's because G of 5 is clearly negative. G prime of 5 is positive 2. But we need to figure out where G double prime falls. And so to figure that out, we're going to have to differentiate G prime. So since G double prime is the derivative of G prime was f of x, so the derivative of f of x is f prime x. And so whereas on the previous problem, when we're evaluating f of 5, we're going to report back the y value that we see on the graph. If we want f double prime of 5, which is f prime of 5, that we are going to be looking at the slope. Now, I don't think we're going to be able to calculate the slope without knowing the equation of this function. But I've got a sneaking suspicion I know what's going to happen here. If I look over at that graph, I can see that at 5, you don't ever want to say, that we know for sure, but it sure does look like that is a local maximum there, and therefore that slope is 0. Let's try that again. There we go. Okay, so key points here. G of 5, that's negative. Okay, G of 5 is negative. G prime of 5 is positive. G double prime of 5 is 0. Okay, so if we're going to go from least to greatest, the smallest one has got to be the negative one, which is G5. So G5 is the smallest, the least. Okay, the next one's going to be the 0 one, that's G double prime. And then the biggest one will be the positive one, which is G prime. Yeah, that one's a pretty tough problem too. But that's it. And that is going to do it for tonight's homework. Please let me know if you have any further questions. I'll be happy to go into more detail on any of these problems. But if not, y'all have a great evening, and I'll see you next time.